So,
are you doing lecturing at the university at the moment?
Yes. We're in session and we are doing our work here.
Yeah, great.
Hello, Afodum. Hello, Afodum. Well, ladies and gentlemen, I think we have to start off this seminar. It is just for 1 hour and yeah, the presenter is already online waiting for us. So we don't have to keep her waiting. We can start while others join as we progress. So today, the 15th of July, 2025, we are to listen to one of us, Dr. Jielai Zhang. Jielai Zhang is a very popular face in Africa. She has been presenting several things to the African community, especially the community of space scientists and astronomers. So Jielai, I think you are just coming home because we see it as a homecoming for you. And you are welcome to this series of our FAST4Future.
Sorry, I just have to do a quick restart of my Zoom. I'll be back on in 1 minute while you finish the introduction. Apologies. I can't seem to screen share until I restart my Zoom.
Okay.
Good morning, everybody. My prof.
Yeah, good morning. How are you?
Good morning. Fine, sir. Sorry, my MTN is giving me a problem. So I have to recharge for Airtel not to get connected.
Okay, it's all right.
Yeah.
Yeah. Welcome back, Jielai. So as I was introducing, Dr. Jielai Zhang is an astronomer that earned her PhD from the University of Toronto in Canada. But at the moment, she's working with Swinburne University in Australia. And today, she's going to present to us on a topic on the Dragonfly Telephoto Array, which she has been working on since her PhD degree program. So, Dr. Jielai Zhang, you have the floor. You have about 1 hour to present to us. And I will plead that you can also give us some few minutes to talk about your center and your university so that those of us from the African end can have a feeling of what you are doing and what your institution is actually known for.
Okay.
So
sounds
now
great.
You have just 1 hour for your presentation. Thank you.
Thank you. Hello, everybody. Thanks, Finbar, for that introduction. And it is indeed great to connect again with my African colleagues. We've had a really great time working together in the past for a summer school called the Pan-African School for Emerging Astronomers, or PAISEA. So as requested by Dr. Finbar, I will talk a little bit about the different institutes that I have worked at before I start my presentation. So the presentation I will be giving today is about the Dragonfly Telephoto Array. And this work was carried out during my PhD at a number of different institutes, all in Toronto in Canada. The university is called the University of Toronto, and there isn't just one astronomy topic that is done very well at the University of Toronto. There's actually many, from galaxies to exoplanets to cosmology, star formation, instrumentation, fast radio burst, you name it. There's some really good work going on there. At the University of Toronto, there are also 2 other institutes. One is called CETA, the Canadian Institute for Theoretical Astrophysics. This is a center where there's lots of researchers who do theoretical astrophysics, where they use computers and mathematics to simulate and make predictions about the universe. Also at Toronto is the Dunlap Institute for Astronomy and Astrophysics. This is a mainly instrumentation organization where they build telescopes, design telescopes, build instruments, design telescopes, design instruments. And so the University of Toronto was an excellent place to do my PhD, where there were a lot of observers, as well as instrumentationalists and theoretical astronomers coming together. Since then, I have moved around to different places, including where I'm currently at, which is the Swinburne University of Technology. That's in Melbourne, Australia. Similar to Toronto, there's a lot of different areas of research that are done really well at Swinburne, including galaxy formation, star formation. Transient astronomy is a really, really big area of research at Swinburne, which is what I'm currently working on now. Transient astronomy is the study of how things are changing very quickly in the universe. We study things like supernovae and fast radio bursts, kilonovae, if you've heard of some of those things. I won't go into detail about them since it's not the topic of my talk today. Also at Swinburne is an institute called OzGrav, and this institute studies gravitational waves and transient astronomy. So it's a very vibrant place to be, just like Toronto. All right, so that's my self-introduction and the institutes that I'm affiliated with and where I did this work. I'll move on to my main talk. So I don't know too much about those of you that are listening in today, but I would like to, I hope that the level at which I'm talking is at the right level that you're all at. And to help me make sure that it is, could I ask you to put into the chat what you hope to get out of today and what you hope to learn? And also during the presentation, if you have questions, feel free to type it into the chat as we go. I've got the chat open, so I should be able to see it as we go. And does that sound okay?
Yes, that's okay.
It's okay.
Excellent.
That's okay.
All right. So if you can put into the chat what you hope to get out of today's presentation, I would really appreciate that. So, today's talk will have two main sections. The first section, I'll talk about why we build telescopes at all, and in particular, why we built the Dragonfly Telephoto Array, which is a telescope. And then the second part of the presentation, I'll talk about some of, in particular, especially one very cool discovery made by the Dragonfly Telephoto Array. So firstly, why do we build telescopes and why did we build the Dragonfly Telephoto Array? So why do we build telescopes? If you're interested in astronomy, which I assume you all are since you're here listening to this talk today, you might know that astronomers have been building larger and larger telescopes over time. And the current cutting edge generation of telescopes, the largest ones currently that have been built are at the 10-meter scale. Can you see my mouse when I move my mouse?
Yes, we can see it.
Okay, excellent. So yeah, the largest current generation of cutting edge telescopes is at the 10-meter scale. And the next set of telescopes that are being planned to be built or currently under construction are on the scale of 30 meters, which is a lot bigger. And so historically, there's been this trend to build larger and larger telescopes. Can anyone tell me why we're trying to build larger and larger telescopes? How does that help us with astronomy? So there's going to be 3 points where I ask your questions in today's talk, and I hope I can get some answers. Anybody? Any ideas? You don't have to be correct, just any ideas you might have. Just pop it into the chat, or you can take yourself off mute and also say it. We build larger telescopes to increase the resolution of the observing object. Anybody else? Thanks for that, Steve.
We build telescope in order to look deeper into space.
Look deeper into space?
Yeah, beyond what our naked eyes can see.
Thank you, Afodum. Yes. Oh, you cannot hear? Aman cannot hear me. Is that right? You can't. Can Finbar or Afodum, can you help Aman with the audio issue at all? And Chitembwa, sorry if I said your name wrong. Yeah, the resolution purpose. Excellent. So that's for the clear resolution as earlier suggested. Thank you, Julius, as well. You're all absolutely right. There are two main reasons that you've covered for building larger and larger telescopes. The first is resolution. If you have a larger telescope, then you can see a sharper image and you can see more detail in your image, which allow you to understand the universe better. The other reason is if you have a larger telescope, it's like having a larger light collecting bucket. And as Afodum says, that allows you to see fainter objects, because to see the fainter objects, you need to collect more light to be able to see them because they're so faint to begin with. So that's what's been happening for the last few hundred years since telescopes started being built. We're building these larger and larger telescopes. However, it turns out that larger telescopes doesn't help see faint, fuzzy, or spread out things. What does that mean? So a larger telescope, yes, allows you to see better resolution. So you can tell two stars that are very close together, you can tell them apart if you have higher resolution. And if a star is fainter, then a larger telescope will allow you to see it. And so if you build a larger telescope, this picture will get filled with more and more stars as you see fainter and fainter stars, and the picture will become more and more crisp. However, in this picture, if we also see this galaxy here, which happens to be the Andromeda galaxy, and there's also this little dwarf galaxy here as well. And you can see that the outskirts of this galaxy, for example, are very, very faint. And as you get out further, they get fainter and fainter. It turns out a larger telescope doesn't allow you to see this faint, spread out light. That is light that have low surface brightness. And you can't see this better as well. So you can't see fainter and fainter surface brightness things. So larger telescopes doesn't help with this. And that's the reason why for the last 40 years, actually, even though we've been building better and more cutting edge telescopes, we actually have not been able to observe lower and lower surface brightness objects. Before I go on to explain what it takes to see low surface brightness objects, I'm going to motivate why we want to do that in the first place. So there are when the universe is not just full of dots and stars and point sources, it's also full of things that have low surface brightness, things that are faint and spread out. In fact, some of the largest structure in the universe is of low surface brightness, and one of them is called the cosmic web. This is the largest structure in the universe. This is not an actual picture of the cosmic web. This is a simulation. So in this simulation, one of these dots, for example, is a whole entire galaxy containing billions and billions of stars, where each star can be something like our sun with multiple planets orbiting around it. And so this is a huge patch of the universe. Based on our understanding of how the universe evolved, we believe, based on simulations, that galaxies are not randomly distributed in the universe. Instead, they are clustered together and form a spider-like filament structure that we call the cosmic web. We haven't directly imaged something like this before. However, if we look at the positions of the galaxies that we observe, one galaxy by one galaxy, and then put it all into a map, it does seem to follow a cosmic web structure. But if we're able to directly image the cosmic web, which is very low surface brightness, it would really help revolutionize our understanding of of the evolution of the universe, which is very exciting. So that's one motivation. On the smaller scale is dust. So it turns out the universe doesn't just have galaxies and stars. It's also populated by clouds of gas and dust. And this gas and dust is the material out of which stars are formed. It's the basic raw material out of which anything that shines, which are basically stars, is made out of in our universe. However, so this picture is of the Milky Way as observed from Earth. We're looking through, so the Milky Way is a disk galaxy and we're looking at an edge on. And all this dark stuff is dust in the way that is blocking the light from behind. However, we can't see all the gas and dust in the universe because some of it is very faint and low surface brightness. So this is another area that having a low surface brightness telescope can really, really help. The next bits of motivation I will go through a little faster. So galaxies I already talked about. If we can understand if we can observe the edges of galaxies, that will also help us understand how galaxies evolve over time and how they came to be the way they are. It turns out we can study planets as well. For example, we all know Saturn has a ring around it, but it turns out Jupiter also has a ring around it, but it's just harder to see because it's low surface brightness. Theories are there's rings around other planets as well, but we don't know if they're there or not because we don't have the means to be able to observe to such low surface brightnesses. So there's all these different reasons, and I have not even given you a complete list of reasons why observing at low surface brightnesses would be very, very interesting for our understanding of the universe. But other than these specific reasons why it's specific reasons and specific objects that are interesting to observe, being able to just see fainter things allows us to open up a new parameter space. And it's this new parameter space that allows new discoveries, things that we haven't even imagined might be there because we hadn't seen it before. And that's one of the most exciting things about working on a telescope that allows you to see see the universe in a way that has never been seen before. All right, so that's the motivation for wanting to see low surface brightness objects. Now I'm going to go back to, well, why doesn't larger telescopes help us see fainter, fuzzy objects of low surface brightness? And what does it take to see the universe in low surface brightness? So the job of a telescope is to collect as much light as possible and then to focus that light into an image and then take a photo of it. To collect as much light as possible, we build larger and larger telescopes. We've already talked about that. And then to focus the light, we use a mirror. Or we can use lenses as well. However, you can't really build lenses bigger than about 1 meter. If you try to build a lens that's bigger than about 1 meter, it will deform and warp under its own weight, and then it will not be able to focus light properly anymore. And so if you want to build a telescope that's bigger than 1 meter, such as 10 meters or 30 meters, you need to build a telescope with mirrors. When you build a telescope with mirrors, the light will come in, reflect off the mirror, and then focus at a point either up here, so the light will come in and then bounce and focus at a point up here, or you can put another mirror here to further focus the light and then go through the middle of the mirror to behind here where the camera sits. So that's how a mirror telescope can work. The problem with these mirror telescopes is that what you would really like is the light to come in and not to have all this stuff in the way. If you have all this stuff in the way, the light isn't able to just purely focus. Some of the light will get diffracted and scattered by these structures, as well as actually by the mirror itself, which have a micro roughness. And what that does to your image is it can make the image have things that look like this. So let me know if you've seen pictures like this where you got this weird halo and structures around bright stars. Have you all seen something like this before? Type yes or no into the chat. No? Thanks, Julius. Other people? No. Okay, so this is fairly new to everyone. Any others? No? Thank you, Jude. Thanks, Offerdom. Yeah, so typically you can see this around the really brightest stars and you can't see them around the dim stars. And so even if your telescope has this kind of effect because of has this kind of effect because of the structures in the place around the mirrors to hold the secondary mirror up or to hold the camera up, you don't usually see them unless you have a picture of a really, really bright star. And so they took a picture of a really bright star to illustrate the point. So these things, the 4 spikes can be because of these spikes of the telescope. This particular image is not taken by this telescope, so it's not exactly the same. But a lot of telescopes have 4 spikes to hold up the secondary mirror or camera. And so you see this, and then there's all these other effects as well, because the light isn't able to purely focus to the central point. Instead, it gets diffracted by all these structures. And so a mirror is not great. In fact, there was a study done on a telescope to try and remove some of these effects. And they found that even though you don't see this structure around all the stars, it's there, it's just faint. And they found that at a certain surface brightness of 29.5, so this is fainter and this is brighter. As you get to the really, really faint end, every single pixel on the image is contaminated by the scattered and diffuse light as a result of the telescope structures and the mirror, which is not good at all, because imagine if you're trying to find a galaxy in this image and it's low surface brightness. When you find something, you don't know if it's real or it's just the result of these things superimposed on top of each other. I don't say this to give large telescopes a bad name. Large telescopes are absolutely spectacular, and they're really, really good at what they do. That is seeing things at high resolution and seeing things that are really faint, that are point sources. But it's just not good at low surface brightness observations. So just to make sure I don't give large telescopes a bad name, and to emphasize that I think they're absolutely great. A telescope called the Vera Rubin telescope was recently publicized its first look images, and you can see they're absolutely spectacular. The amount of detail that you can see in the bright regions of these galaxies, the amount of faint stars that you can see is absolutely spectacular. It's just that if we try to see the fainter surface brightnesses, this telescope isn't going to be the most suitable. So if we want to see things like the cosmic web, faint planetary rings, outskirts of galaxies, this telescope is not able to do that. So what do you need to see low surface brightness objects? Well, we talked about how mirror telescopes cannot really achieve this because they have all this stuff in the way, amongst other reasons. What about lensed telescopes? Well, it turns out lens telescopes have their own problems too. So for example, have you ever taken a photo and you see these lens flares? Please put yes or no into the chat. And if you're a photographer who has artistic talent, you might even intentionally include some of these because they look kind of cool. Thanks, Julia. So you've seen it before. Chitwemba hasn't. Ofudum has. Chinedu has. Thank you. So some of you have seen something like this. Some of you haven't. If you haven't seen this before, if you take your phones, they are a lens telescope. So if you don't look at the sun, but point your phone at the sun at an angle and see if you can get some of these lens flares. Should be fairly easy if you point it at the sun. But again, don't look at the sun because that will hurt your eyes. So what you can imagine these lens flares also, excellent. Thanks, Chitembwa. Yeah, it'll be fun to try. So you can imagine these lens flares are also bad if you want to see low surface brightness things. Imagine if you saw a galaxy and you're like, oh, is it a galaxy or is it just a lens flare? However, I'm going to talk about what causes these lens flares, and it turns out there's a way to reduce them, which is one of the foundations of the design of the Dragonfly Telephoto Array. So so this is a camera that I drew. That's why it doesn't look very cool, because I drew it. So let's say you're trying to take a photo of a star or anything you want to take a photo of. The light comes in through the lens and focuses it, and it's supposed to focus onto this point on the image. So the light comes in from outside the camera and through the lens, and it's supposed to focus on this point in the image. However, as the light comes through, when it goes from the lens back into the air, or when it goes from the air into the lens, there is a surface where the refractive index changes quite drastically, because the refractive index of the lens is different to the air. In fact, this refractive index change is what helps focus the light. But in our case, because of that change of refractive index, a very small fraction, so most of the light still goes through and is focused, but a very, very small fraction of the light can bounce off this sharp, fast refractive index change surface. And if it does it again here, an even smaller, so most of it will go out, but a very small part of it might bounce back. then you can get another image of the same object at a different spot, which is what causes these lens flares. So in order to reduce lens flares, what we need to do is reduce the amount of reflected light at the lens-air interface. So some of you have seen pictures like this of like at the outside with the sun, but it exists in astronomical images as well. It can look like this, or it can look like this or like this. And so if you find a galaxy, or what you think might be a galaxy, you cannot be sure if it's a galaxy or just one of these lens flares, which means that this is not great for low surface brightness observations. So I have a picture of a dragonfly. This is a bit strange, and innovation and ideas in science come from all sorts of different places. And the solution to fixing this lens flare problem actually came from an astronomer called Peter van Dokkum, who is at Yale University, and he does astronomy, but in his spare time, he also likes to photograph dragonflies, which are really difficult to photograph. And so to photograph them well, he actually it keeps up to date with different types of cameras and lenses. So he realized that Canon released a lens that minimizes these kinds of ghosting effect because of sports photography. In sports photography, you want to take photos in really bright environments because then you can get the sharpest, best photos. But then you get these lens flares, which ruin the sports photography. And so Canon developed this lens that reduces these kinds of internal reflections. The way it does this is normally when you have a lens, the interface between the air and the lens is very sharp. So the light comes in and then it will get, most of it will go through, but some of it will get refracted. But the Canon lens surfaces are coated with this sub-wavelength nanostructure, which if you use an electron microscope, they look like little mountains sitting on top of your lens. And as the light comes in, instead of seeing a sharp change in the refractive index, it sees a gradual change in the refractive index as it slowly sees more and more lens. And what that does is it tricks the light to not bouncing off because there's no sharp change in the refractive index. And so this was the theory that this was going to help us be able to image low surface brightness objects with a lensed telescope design. So we decided to go out and buy some of these lenses and put cameras on the backs of them, put them in New Mexico and give it a try. And it seems to work. And in that it has less ghosting effect and lens flare. However, with just the Canon lenses are quite small. And so even if they can see, if they don't see these lens flares, it still doesn't collect enough light to see faint things unless you stare at something for like 10 years or 20 years. And so to increase the light collecting area, we bought a lot of lenses so that their light can be added together. And this is a photo of me from a while ago. So I look a little younger. No, I still look pretty similar. We put a lot of these lenses together to make what is called the Dragonfly Telephoto Array. And this was a partnership between Toronto University and Yale University. And after a lot of work putting together the physical telescope as well as the software to optimize for low surface brightness image processing, it works. So these are some examples showing how well the Dragonfly Telephoto Array works. The first two panels are galaxies, and the colored image in the middle is what is another telescope's photo of these galaxies. And you can see they have higher resolution because they're taken with larger telescopes, and they look really nice. However, you can't see them beyond a certain radius. Because beyond a certain radius, they become really, really faint. The black and white picture that's put on top of the colored picture is the picture taken by the Dragonfly Telephoto Array. You can see the galaxy actually extends way beyond what these other telescopes can see, into these very low surface brightness regions that only Dragonfly can see. The third panel here is an image of really, really faint dust in the Milky Way galaxy that also hasn't been imaged before because it's so faint, and nobody else could really see everything clearly, or if they see something, they can't be sure if it's real or just as a result of the telescope issues. So this was really exciting because for 40 years, astronomers haven't been able to see to fainter surface brightnesses, and with the Dragonfly Telephoto Array, we suddenly could see 10 times fainter in surface brightness. All right, so that is the end of the first section of my talk about why build telescopes and why build Dragonfly. Build telescopes because you can see fainter, you can see sharper, and you can do that by building larger telescopes. But if you want to see lower surface brightness, you need to build something like Dragonfly with lenses that reduce the lens flare effect. So that's the first section of my talk. If you have any questions, you can pop them into the chat. Or you can ask them at the end as well. That works. So the second part of my talk is to talk to you about one of the coolest discoveries made by Dragonfly. So this is a discovery in the true sense of the word because we were not looking for this. We did try to look at the outskirts of galaxies where it's really faint. We did try to look at dust because we knew there were faint dust that people couldn't observe before. We even tried to look for planetary rings, although we didn't end up finishing that project because we got very distracted with this cool new discovery that we didn't expect, that I will now tell you about. This discovery is about galaxies, and so I first need to talk a little bit about galaxies. What is the diameter of Dragonfly? Each of these, thank you for the question, Afudum. Each of these is about 40 centimeters, and then we got 48 of them together. So 48 times. There's about 1, 2, 3, 4, 5 times 40 centimeters across. And we already have 2 of them, and they're building more. So yeah, to explain to you the cool discovery, I have to first talk a little bit about about galaxies. So galaxies don't come all the same. Some of them, they can have different sizes, brightnesses, different shapes as well. And so 2 key properties of galaxies is their brightness and their size. And for a long time now, we've been collecting galaxies and measuring their brightnesses and sizes. So this is a plot of galaxy sizes and brightnesses. I just point out, for example, this is brighter, this is fainter, and this is smaller, and this is larger. So these are the brightest and largest galaxies. these are the brightest and smallest galaxies. These are the faintest but largest galaxies, and faintest and smallest galaxies. And this is where the Milky Way, our own galaxy, sits. I have a question for you. Which one do you think is, which section of this plot shows galaxies of the lowest surface brightness? Is it this corner, this corner, this corner, or this corner? I think I can, do I have a pen? Yes. Let's say this is 1, 2, 3, 4. Which corner do you put into the chat? Which corner do you think has the lowest surface brightness galaxies? I know there are no galaxies here, but if they existed, which corner would those be at? So got 1, 3, 1, 4. Maybe 4. What are others' guesses? Maybe here. Anyone else? So the lowest surface brightness. We got more 3s now. All right, thanks. Maybe some of you are a bit more introverted and don't want to type into the chat. That's okay. All right, so it turns out, actually, how do I need to get rid of the drawing? Clear all drawings. And then, so it turns out number 4, this area has the faintest, largest galaxies. If they're very faint and very large, then their light is very spread out, and that means they look like the faintest surface brightness. So there are no galaxies here, of course, and so of the galaxies that exist on this plot, these are the lower surface brightness. But if galaxies exist here, they would be the lower surface brightness. One of the first things we decided to look at was the Coma cluster of galaxies, because there's lots of cool galaxies in there. And we thought we could see, some of these galaxies we already know that exist. We can see the outskirts of them to try and understand their galaxy formation. But we thought we could also perhaps try to see something called intra-cluster light, which is light of made up of lots and lots of stars that have been able to escape galaxies into the space in between galaxies inside clusters. So we looked at the Coma cluster of galaxies. And we discovered something we did not expect. So this is an actual picture of the Coma cluster of galaxies. It's very zoomed out. Some of these dots are stars in our Milky Way, but a lot of these dots, especially in the middle, are actually galaxies in a cluster of galaxies far away. When we scanned every single part of this image that we took with the Dragonfly Telephoto Array, we found a bunch of galaxies marked by the red boxes all around the Coma cluster that look like this. Little fuzzy blobs that are quite faint. But because the Dragonfly image is so clean and there's no lens flares and no weird things that are like that you don't see things like this that are fake, and we don't see things like this either. And the Dragonfly image is very, very clean. Because of that, we can be sure these are actually real galaxies. And because we were also able to figure out that these galaxies were at the distance of the Coma cluster of galaxies. If we know their distance and we know their apparent size, that is how big they look to us, then we can work out the actual physical size. We can also work out how bright they are and therefore put them on this plot. And when we put them on this plot, they actually populate this space that we thought galaxies didn't exist. We didn't even think there were galaxies there. We weren't looking for them. We were trying to study these galaxies and these galaxies in the Coma cluster, but instead we found this because of the ability of Dragonfly to see at such faint surface brightnesses. So this was a big discovery. We called these galaxies that look like this ultra diffuse galaxies, because the light in these galaxies are extremely diffuse or spread out. This discovery was made with Dragonfly 10 years ago. Wow, it's been a while since my PhD. And these ultra diffuse galaxies are now a very active area of research, with many papers coming out each year observationally, also theoretical studies of them as well, which is really, really exciting. And this is unexpected. And for me, this is kind of one of the coolest things about doing science, when you find something you don't expect when you open up a new parameter space. I hope this is as cool to you as it was to me when we made this discovery. So to give you a better idea of what these galaxies look like, this here is the Andromeda galaxy. It's quite similar to the Milky Way galaxy, just a little bit larger. This is another spiral galaxy. So there are galaxies that are, small galaxies are called dwarf galaxies, and some of them can be quite faint, like this little one up here. But these ultra diffuse galaxies that we found in the Coma cluster are not dwarf galaxies. They're much, much bigger than dwarf galaxies. They're almost the size of Andromeda, which is a huge galaxy, and similar size to other large spiral galaxies. However, they are so diffuse and faint, or low surface brightness, which in and of itself is very cool. But if we start to think about the physics of these galaxies, it's even cooler. To understand why it's even cooler and how it involves dark matter, this will be the last part of my talk to help you understand why it's so cool. So it turns out stars in galaxies are not just sitting there still, they are moving all the time. For spiral galaxies, they're moving in a circle around the middle of the galaxy. So I have a question for you all. If the star is moving around, based on Newton's law, an object moves in the same direction unless it's acted on by a force, right? So if this star is moving in this direction, why does it not just fly off? So please put that into the chat. This is a question for you all. Why does the star not just fly off? Space-time gravity. Thank you, Julius. Anyone else? Centripetal force, gravity at center, constant velocity. Excellent, thanks everyone. Yeah, so force that is directed to the center of the galaxy is acting on it. Excellent, thanks everyone. That's exactly right. There has to be some kind of force, and many of you identified that it's gravitational force, gravitational pull from the center of the galaxy. And this that's right. So, because there's no string attached to the stars, they're freely flying around, but the force of gravity can act without a string. So these stars are not flying off because of gravity. At this point, I like to give an analogy. Like, say you're spinning an object at the end of a string. The faster you spin the object, the harder you have to pull on the string to make sure the object does not fly off, right? And so by measuring the speed of the stars going around, you can estimate the amount of gravity that should be inside of the galaxy that holds on to this star that's moving really fast. So this is actually how something called dark matter was discovered. When people measured the speed of stars, so on the y-axis is the rotational velocity or the speed of the stars going around galaxies, what was measured is way less than what was predicted based on the gravitational pull of all the stars and all the gas that you can see inside the galaxy. And that means there must be something else there that we cannot see that has gravity, and we call that dark matter. One question we might have for the ultra diffuse galaxy, which now I've put to scale. So this is Andromeda. This is Dragonfly 44, one of the galaxies in the Coma cluster, one of the ultra diffuse galaxies. When we measured how fast the stars are going around in this galaxy and then looked at how much gravity is needed to hold on to those stars moving around. And then we calculated what percent of that is stellar mass and what percent of that is dark matter. We found that even though the total mass of the galaxy is the same as something like the Milky Way. This isn't a picture of the Milky Way, it's Andromeda, but it's similar enough to the Milky Way for me to put a picture of it here. It's got similar total mass to something like the Milky Way or Andromeda, but it only has 1% the amount of stars. What that means is that for every kilogram of star, there's 1,000 kilograms of dark matter in here. But in here, for every kilogram of star, there's only 10 kilograms of dark matter, which makes this galaxy very, very dark matter dominated. And if you look up in the news of this discovery, you'll find things like, this is Milky Way's dark twin. It's like the same mass, but it's super dark and super faint. And so this is how science progresses. We find something cool, we find something unexpected, and then we end up with more questions. And we haven't answered those questions yet. Questions like, why did so little star form in a galaxy like this? What makes it different to galaxies like this? And to be able to answer questions like this is going to help us understand galaxy formation and how the universe came to be through this unexpected discovery. So that's the end of my talk. Thank you very much for listening and also engaging with me through the chat today.
Good. Thank you so much, Dr. Jielai, for that very awesome presentation. I'm sure our African students and participants in this seminar are happy to listen to you, and they have gained a lot. So I think we may take some few minutes, maybe about 5 minutes, to ask some questions or comments, and then maybe give some other further clarifications, if any. So
yes,
if one
I already
has any
see
question, you can
some
do
questions. Some questions from Julius and Aman. So Julius's question: in reducing the observed flares, what effect does that process have on the intensity of light measured or observed? I referenced the electron image displayed earlier. That's actually a very, very interesting question. And I have a backup slide that maybe is going into too much detail. So on the x-axis is distance from the center of a star, and on the y-axis is how bright that star looks. So stars are meant to be point sources, but when you take a photo of it, because of the optics and also because of the atmosphere, actually, the light gets spread from where it's supposed to be in the middle out towards the outside. And so some of that outside light makes lens flares. So if you reduce the lens flares, actually that light goes, it means the light is not thrown out of where it's supposed to go. And so it actually makes the center part of the star brighter, or appear brighter, and it means you can see them better. And so in reducing observed lens flares, it does allow the actual object to be slightly brighter, which is not noticeable by eye, but is noticeable by measurement. And it's actually really important when we start to study galaxies and stars and try to measure the actual brightnesses and the actual brightnesses, especially with respect to radius. Second question, how far out can Dragonfly observe? The redshift range of sources it can observe. So how far a telescope can observe is a very difficult to answer question, but it depends on the filter of the telescope. So with the Dragonfly that I showed you a photo of here, it only mostly sees objects that are relatively close. Like the Coma cluster is a little bit far, but we see mostly things that are relatively close. However, there is an upgrade planned to the Dragonfly Telephoto Array to try and observe the cosmic web directly. And to do that, we need to see the very early universe, which is, let's say, at least millions, potentially a few billion light years. Don't quote me on that though, but much further away. Aman, how are light echoes related to ultra diffuse galaxies? You probably saw this slide that I skipped over. Firstly, I'll quickly explain what a light echo is. A light echo is, let's say you have a star that went supernova, and then the light from that supernova can, actually, if I use this, sorry, a lot of slides. Use this other backup slide. Let's say a supernova goes off, then the light obviously travels towards, and let's say we're looking at it from here, the light travels towards us, but it also travels in every single direction. And at some point, the light from the star hits this object. And then once it hits this object, it could reflect or scatter towards us. And then we can see this light sometime later. So what it actually looks like is we don't see these dark clouds yet. We just see the supernova, and then later the light hits this dark cloud, bounces it towards us, and we see this brighten up. So that's the light echo. That's what a light echo is. It's like the sound, it's the same as like someone talks in a really empty place, and then you hear echoes of their sound. You hear their main sound like, hello, 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 hello. The later hellos is because the sound is bouncing off things on the side. So it's the same concept. So light echoes are not related to ultra diffuse galaxies. They're just another thing that has low surface brightness. How is dust related to the cosmic web? Again, not directly, just that they both have low surface brightness. What are stellar halos? Stellar halos are, so if you have a galaxy, something like the Milky Way, most of the stars is in a pizza-shaped disk shape. However, there's also stars that's more in a spherical shape around the galaxy. It's just fainter, so it's harder to see. And that some galaxies have more and some galaxies have less, and that's called the stellar halo, the stars that are not in a disk shape. Does it mean the size of a galaxy has no effect on its brightness? Yes, that's right. It turns out galaxies can be large and bright, or small and bright, and so there's all sorts of galaxies. It's a zoo out there. Is this currently used to study, say, dark matter distribution of density fluctuations and possibly give information on the bias? I'm not sure what the second part of your question means, but the first part of the question is it currently used to study the dark matter distribution. Just by studying the dark matter distribution inside galaxies, I guess it's a way of studying dark matter distribution and where it's situated in the universe. So yes, is it used to study density fluctuations? Not directly, but if we can image the cosmic web, then it will get us closer to be able to study density fluctuations directly. What are lower light surface objects? Like, for example, how is galaxy, so what's a lower light surface? So lower surface brightness. So the lower surface brightness objects. What are low surface brightness objects? So for example, when you look at a galaxy, like this middle, when you look at stars, they look like point sources, right? But when you look at a galaxy, there's no points. And so when you measure the brightness of a star, you just add up all the brightness of the star, and then you can say the brightness of the star is X, Y, Z. But the brightness of a galaxy, yes, you can add it all up and say what is the total brightness of a galaxy. But if you want to be able to describe the brightness of a galaxy here versus the brightness of the galaxy here, it's obvious it's fainter here but brighter here. Then you can't really add it all up, because where does it end? You can measure the brightness per area, and that's the surface brightness. So a lower surface brightness object is just an object where the brightness per area is low. I hope that answers that question.
Yeah, thank you so much, Dr. Jielai. I know if we continue, you will be here for the next 2-3 hours answering questions. So I think we have to call it a day now so that we release you to enjoy your night. You know, we are in our midday. We are in the midday now, so we are enjoying the day, but I know it is a big stress for you doing this kind of thing in the night where you are. So once again, I thank you so much for making out time to be here for this seminar. And I do hope that when we call on you again, you will respond and talk to us. You are one of us, and we see you as our own.
Excellent.
So thank you so much. Yeah. Well done.
Thank you, everyone. And thank you very much for your engagement in the chat as well. I really enjoyed your answers and your questions. Have a good day, everyone. Thanks, Finbar.
Bye-bye.
Yeah. Bye, Jielai.